Square roots, radical notation. Before we get into radicals, we're going to review a little bit. For instance, 4x cubed minus 5x squared plus 7 is equal to 21 is obviously an equation that has an equal sign. But equations, like expressions, polynomials, and so forth, are made up of terms. Terms are separated by addition or subtraction, or an equal sign, if you will, in this example. For instance, in this example, 4x cubed is a term, negative 5x squared is a term, 7 is a term, and 21 is a term. Terms are separated by addition or subtraction or an equal sign, like I said, if you will. And they're made up of factors, which are separated by multiplication and division. So 4x cubed, two things being multiplied, made up of two factors. Every factor has its own exponent. So if an exponent is not shown, we know it's automatically 1. So if that exponent of 3 only belongs to the x, the factor 4 has its own exponent, an exponent of 1. So we know what exponents are. We know where to identify them, where they're written, kind of upper right-hand region. A power is made up of a base and an exponent. So x squared, x is referred to as the base, what's being raised to the exponent 2, and that exponent tells you how many times the base is multiplied by itself, so that would expand out x times x. Likewise, y to the 5th would expand out as y times y times y times y times y. Cubed, that exponent of 3 only belongs to the a. The factor 3 has its own exponent, so when you expand that out, it expands out to 3 times a times a times a. However, if you put parentheses around the 3 and a, now everything inside the set of parentheses is being cubed. In other words, 3a is the base, so it gets multiplied by itself 3 times. Another common mistake students make in math is thinking that negative 3 squared is equal to a positive 9. It's not. We know that anything negative, the way it's written in this case anyway, anything that's negative is actually being multiplied by a negative 1. So if we write it out like that, we see that exponent of 2 only belongs to 3. That factor negative 1 has its own exponent, so when you expand it out, negative 1 times 3 is equal to negative 9. However, if you put the negative 3 in parentheses and then square it, now everything inside the set of parentheses is being squared along with the negative, so that becomes negative 3 times negative 3, which is a positive 9. So paying attention to the details is going to be extremely important in this chapter, knowing what you can and cannot do. Which brings us then to radicals, what we're going to be working with. A radical is made up of two different parts, an index and a radicand. We know the radical notation or symbol. Whatever is inside the radical is called the radicand, and the index, denoted by a lowercase n, is some number that tells you what type of radical it is. The most common radicals we're going to work with are square roots, so they have an index of 2, cube roots, cube root of 3, and obviously we can have any root though, 5th roots, 6th roots. Any index other than 2 must be written. In other words, square roots, you do not have to show the index. For instance, if I gave you the square root of 5, this radical, the radicand is obviously 5, but an index is not shown, which means it's automatically 2 or automatically a square root. Any index other than 2 must be shown. For instance, the cube root of 5. Now we're going to learn how to simplify radicals, which is going to be a big part of this chapter, but in the meantime, we need to review some certain numbers, some sets of numbers, perfect squares and perfect cubes, which you need to know and be familiar with in order to simplify radicals. First of all, perfect squares, numbers that you can take the square root of and get an integer or a whole number. For instance, the square root of 1 is 1, the square root of 4, 2, the square root of 9, 3, and so forth. Up to square root of 169, 13, square root of 196, 14, square root of 225, 15. And square root of 625 is 25. Now these are the most common perfect squares for the examples you're going to see. But they can be certainly larger than this. You will certainly have perfect squares other than these show up in problems from time to time. But these will get you through the majority of the examples you're going to see. So you need to know these perfect squares just by looking at them. Same thing as perfect cubes. Perfect cubes, numbers that you can take the cube root of, and it works out to be a whole number or an integer. Now these obviously you get larger a lot quicker since you're multiplying 3 numbers together, and they're not as common as perfect squares. So there's not as many of them that you really need to know, but once again you can see any perfect cube either other than what's on this list. The cube root of 1 is 1, cube root of 8 is 2, cube root of 3, or cube root of 27 is 3, cube root of 64 is 4, cube root of 125, 5, and of course the cube root of 1000 is 10. So with those perfect squares, perfect cubes, it'll help us simplify radicals that have a number or a constant in them. So the first thing you want to do is, of course, identify the radicand, identify the index, so you know exactly what's going on in the problem, what type of radical you have. So in example 1, the radicand, of course, is 36. An index is not shown, so we know that it's 2, so the square root of 36. To simplify a radical that has a constant, begin by asking yourself, is that radicand a perfect nth root? And in this case, example 1, is 36 a perfect square? And yes, it is. It's on the list. We recognize it. We know the square root is 6, so that's it. The square root of 36 is 6. Example 2, similar problem. The radicand is 64. The index is 3. This is where it's important to pay attention to what type of radical you have, because 64 is actually both a perfect square and a perfect cube. The index is obviously 3, asking us to find the cube root of 64. So from our list, determine, is 64 a perfect cube? And yes, it is. So the cube root of 64 is simply 4. Now most radicals we work with are not going to be perfect roots. For instance, number 3, the square root of 75. 75 is not a perfect square. So what we want to determine then is if it has any factors that are perfect squares. So we reviewed factors earlier. If it helps you can either even write them off on the side of your paper a little bit. The factors is 75. Well, of course, 1 is always a factor. 3 and 25, and 5 and 15. So 1 isn't going to help us out at all. We want to choose any factors other than 1 that are perfect squares, perfect cubes, perfect squares in this case. So obviously 25 is a root that's a perfect square, so we're going to rewrite 75 as 3 times 25. Still one term. We just broke up that one term into 2 factors now, 3 times 25, which that allows us to then rewrite each factor into its own radical, allowing us then to simplify each radical individually. Well, we still can't simplify the square root of 3, so it remains where it's at. The square root of 25 obviously is just 5. So once we take the square root of it, it no longer belongs inside the radical. 5 comes outside the radical, and we like writing it out in front, so we can clearly see that's just 5. 5 times the square root of 3 is the simplified radical. Example 4, square root of negative 16. Well, we know 16 is a perfect square, but not negative 16. So we might try and play with it a little bit. We just said a little while ago that anything's negative is actually being multiplied by negative 1, so we could write it as negative 1 times 16, allowing us then to once again break up each factor into its own radical, allowing us to take the square root of 16, which is 4, but we still have that radical, square root of negative 1. Well, 1 times 1 is a positive 1. Negative 1 times a negative 1 is a positive 1. So we cannot multiply 2 identical real numbers together and get a negative number. In other words, we cannot simplify that radical. Which brings us to a rule here. If the index is even and the radicand is negative, there's no real number solution. So here, index is 2, even number, the radicand is negative, so what you would tell me here, there's no real number solution. Now that's important, real number. There is actually a solution to it, it's just not a real number solution, which we don't know what it is at this point. Later on in this chapter, we will introduce a set of numbers, the non-real numbers or imaginary complex numbers, that will allow us then to simplify this further. But up until that point, you would just state no real number solution. Example 5, the cube root of negative 16. This one does have a real number solution. The index is odd, so we can rewrite that as negative 1 times 16. 16 is not a perfect cube, but it does have a factor. We can rewrite that as 2 times 8. So break up negative 16 into 3 factors, negative 1 times 2 times 8, allowing us to take the cube root of each individual factor. We could show that by rewriting each factor in its own radical, or we can just work or simplify each factor working from left to right, beginning with negative 1. The cube root of negative 1 is negative 1. We cannot do anything with the cube root of 2, so it's going to remain in that radical, and the cube root of 8 is 2, so it comes out in front, which simplifies to negative 2 times the cube root of 2. Example 6, negative square root of 1 over 98. Always simplify it if you can. Obviously we cannot reduce this fraction, 1 over 98. The index is 2, so square root, and we see a negative there, but the negative is not inside the radicand, so the radicand is not negative. So we still only have one term in the radicand, one term with two factors, so once again what we're allowed to do is rewrite each factor into its own radical, allowing us then to simplify each, keeping in mind that that negative is just going to carry through. Begin with the numerator, square root of 1, of course it's just 1. The denominator, square root of 98. 98 is not a perfect square, but it does have a factor that's a perfect square. 2 times 49, allowing us to take the square root of 49, which is 7. We can't do anything with that 2, so it remains exactly where it's at inside that radical. Number 7, cube root of 108. So the index, of course, is 3. The radicand, 108. 108 is not a perfect cube, so we want to determine if it has any factors that are perfect cubes, and it does. We can rewrite it as 4 times 27, allowing us to take the cube root of 27, which is 3. We can't do anything with that 4, so it remains exactly where it's at inside that radical. So 3 times the cube root of 4. And number 8, square root of 45. Index is 2, radicand 45. 45 is not a perfect square, but it does have a factor. 9, that is a perfect square, so rewrite it 5 times 9, allowing us to take the square root of 9, which is 3, and that 5 remains exactly where it's at inside the radical, so 3 times the square root of 5. So simplifying a radical with a constant, but obviously we're going to have variables as well. To simplify a radical with a variable, identify the radicand, identify the index, and then what we're going to do is determine how many times the index would divide into the variable's exponent without going over. That would be the variable's new exponent outside the radical. Any remainder would be the variable's exponent inside the radical. Which sounds a little confusing, but once you see an example or two, you're going to catch on pretty quick. Example 1, obviously the radicand, x to the 6. The index not shown, so it's automatically 2. So to simplify a radical with a variable, determine how many times the index would divide into the variable's exponent without going over. So 2 goes in the 6 3 times, so that's going to be x's new exponent, x cubed, outside the radical. And in this case it divided in evenly, so we do not have a remainder, which means we're done. The square root of x to the 6 is x cubed. Example 2, the cube root of a to the 7th. The index 3 goes in the 7 2 times without going over, so that becomes a's exponent outside the radical, a squared. But in this case we do have a remainder of 1. So that's going to be a's exponent still inside the radical, a to the first power, which of course we don't write, so we would just leave that written as a squared times the cube root of just a. Number 3, the square root of 9, x to the 15th. Look at the radicand, know what you're working with. We don't have any addition or subtraction, so that's all one term still in the radicand. One term made up of two factors, 9, x to the 15th, so we know we can just take the square root of each factor, beginning with 9. The square root of 9 is simply 3. The square root of x to the 15th, 2 goes in the 15, 7 times without going over, with a remainder of 1, so that's going to be x's exponent still inside the radical, x to the first power or just x. And example 4, the cube root of 32, x cubed, y, z to the 10th. A lot going on in the radicand here, but it's still all one term. It's one term made up of 4 factors, so take the cube root of each factor beginning with 32. 32 is not a perfect cube, but it does have a factor that's a perfect cube, 8. The cube root of 8 is 2. We cannot do anything with that 4, so it remains inside that radical. Go on to the next factor, x cubed. Well, 3 goes into 3 once, so that's x's exponent outside the radical, x to the first power, or just x, and no remainder, so we're done. The next factor, y. Y's exponent is 1, so of course the index does not divide into 1 at all. In other words, y cannot be simplified, so it remains inside the radical. And z to the 10th, 3 goes in the 10 3 times with a remainder of 1. So 2xz cubed times a cube root of 4yz, the simplified radical.